Your fingers close around a rock, cool stone, rough edges, exactly the weight your palm expects. Your arm cocks back and snaps forward, releasing everything your shoulder can generate. The rock rips through Earth's thick air. It climbs curves and slams into dirt 40 meters from your boots. Dust kicks up where it lands, marking the exact edge of your strength. With Mars' gravity pulling at just 38% of Earth's strength, the exact same throw that sends a rock 40 meters on Earth would carry it more than 2.5 times farther on Mars, over 100 meters without the thrower getting any stronger at all. 40 meters becomes 100, same arm, same rock. A different planet rewrites the ending. Mars operates under a lighter pull entirely. Surface gravity there measures 3.71 meters per second squared. That's less than 40% of what human muscles evolved expecting. A body weighing 100 kilograms on Earth weighs only 38 kilograms on Mars. Everything you lift, swing, or throw answers to a weaker hand pulling downward. Boots that felt heavy on Earth suddenly feel like they belong to someone else entirely. Air barely exists to slow anything down either. Mars' atmosphere sits near 610 pascals. That's roughly 1% of Earth's sea level pressure. Drag that normally steals speed from a thrown rock almost disappears completely. Your rock climbs into nearly empty sky. It traces a longer, flatter arc across the rust-colored ground. The arc hangs there far past the moment your instincts expect it to drop. Thin air, weak gravity, a rock with nowhere fast to fall. Two invisible forces conspire against every assumption your body carries from Earth. Weak gravity refuses to pull the rock back down quickly. Thin air refuses to grab the rock and slow its flight. Both forces stack together, multiplying the effect far beyond what either one alone could produce. Neither force announces itself, yet together they rewrite an entire afternoon of simple physics. Most people picture low gravity as a cartoon effect. Astronauts bouncing in slow motion, objects drifting through soft, dreamlike air. That image treats Mars like a mood, not a measurable fact. Reality refuses that vagueness, completely replacing it with a hard number anyone can check. Weaker gravity doesn't create a feeling. It creates an exact calculable multiplier. Range scales directly with the inverse of gravity's pull. That relationship has held true for centuries. Nothing about it stays mysterious once real numbers appear on paper. None of this required inventing new physics or discovering hidden particles. Newton's equations, written centuries before anyone dreamed of Mars, predicted this exact outcome. The same formula taught in introductory classrooms scales perfectly across two entirely different worlds. Simplicity itself becomes the most convincing proof that the universe runs on consistent rules. Engineers rely on this exact math for landings, drops, and bounces on foreign ground. Projectile motion obeys one governing equation. Range equals launch velocity squared times the sine of double the angle. Divide that whole result by gravity's pull. Your arm supplies the velocity term, and that number stays fixed everywhere you stand. Gravity alone occupies the denominator, deciding exactly where the rock lands. Shrink that denominator, and the whole equation shifts instantly. Mars' gravity measures roughly 2.6 times weaker than Earth's pull. Shrinking the denominator by that factor multiplies the entire range directly. A rock thrown at 20 meters per second travels about 41 meters on Earth. Launch it at 45 degrees, and that number holds precisely. That identical throw changes everything on Mars. Same velocity, same angle, same arm doing precisely the same work. The rock now travels roughly 108 meters before gravity finally wins. One planet, one throw, 100 extra meters appearing from nowhere. Numbers like these rarely feel real until measured against something familiar. 100 meters stretches past an entire soccer pitch on Earth. It equals the length of a city block downtown. Watching a rock land that far reframes what a single arm can do. An ordinary toss suddenly looks almost engineered. This isn't some alien trick unique to Mars. Basketball players notice shots arcing differently at high-altitude arenas. Thinner air quietly changes the physics mid-shot. Golfers on the moon watch their drives sail absurdly farther than any Earth fairway allowed. Mars simply stretches that same familiar principle into a planetary extreme. Picture a baseball thrown clear across a football field on Earth. It lands right at the far end zone. Now picture that identical throw sailing across two full fields plus half a third. Nobody trained harder between throws. Nobody added muscle or changed technique. The only thing that changed was the ground itself. Mars handed over that extra distance for free, distance that costs nothing, effort that stays identical. A planet quietly rewriting the outcome of a simple game. Your arm never changes between worlds. Muscles fire the same signals every time. Tendons snap forward carrying the same tension. Fingers release the rock at the exact same instant. Every biological input stays perfectly identical, whether you stand on desert sand or Martian dust. Only the invisible pull beneath your boots decides how this story ends. Watch the rock hang in Martian sky longer than instinct expects. Seconds stretch past where Earth-trained eyes assume it should already be falling. The rock keeps climbing. It keeps drifting. It keeps refusing the timing your body memorized since childhood. Every dropped ball, every skipped stone quietly recalibrates the moment gravity changes. Your eyes track the rock against a pink dust-hazed sky. Something in your chest tightens as the seconds stretch longer than they should. Nothing about the sight matches decades spent catching and judging falling objects on Earth. The horizon sits closer than expected, curving away faster underfoot than instinct allows. Depth perception starts lying the moment gravity shifts beneath you. Distances stretch thin against a sky your brain never evolved to read. Every visual cue you've trusted since childhood quietly stops applying. The rock still obeys physics perfectly, even while your senses insist something has gone wrong. Earth taught your nervous system one specific falling speed. That speed felt absolute universal, permanently built into how objects behave. Mars proves that assumption wrong inside a single thrown rock. The rules governing every game of catch were never universal at all. They were only Earth's local settings the whole time. A thrown rock becomes a survival lesson in disguise. Trusting instinct over numbers gets a colonist hurt fast on Martian ground. Reaching for a dropped wrench follows a different arc entirely. Tossing gear across a work site follows that same unfamiliar curve. Old muscle memory stops applying the instant boots touch Martian soil. Learning that new arc becomes as vital as learning to breathe inside a suit. Future colonists tossing tools across a work site must relearn physics from scratch. Astronauts walking that rust-colored ground will train for arms that suddenly feel superhuman. Adaptation becomes survival, and survival becomes proof that human bodies recalibrate under pressure. The first Martian colonists will carry this lesson before they carry anything else. Training manuals will open with projectile math instead of survival checklists. A rock thrown wrong becomes a dropped tool lost forever across unfamiliar terrain. Getting the numbers right becomes as routine as checking oxygen levels each morning. The human mind, given enough time, rewires its own deepest expectations. Panic gives way to fascination the moment the numbers click into place. A colonist who once flinched at every strange bounce starts predicting distances within weeks. Muscle memory rebuilds itself around a lighter world quietly without conscious effort. Training grounds on Mars will look nothing like Earth's gyms and fields. Simulators will drill new colonists on exactly how far a wrench flies. Every dropped tool becomes a lesson in Martian arithmetic instead of instinct. Bodies raised entirely on Earth eventually learn to think in Martian numbers instead. The strange becomes ordinary the same way any frontier eventually becomes home. That rewiring points straight toward humanity's next physical frontier. Engineers designing Martian sports fields must build around a 38% gravity baseline. Throwing distances, fall speeds, even how dust settles after impact all shift under Martian rules. Every tool and habit humans carry to Mars demands quiet, careful reinvention. Construction crews will measure differently on Martian soil. Athletes will train differently for Martian competition entirely. Children born on Mars will grow up throwing rocks past 100 meters routinely. A throw that would break records on Earth becomes an ordinary afternoon on Mars. Ordinary there, extraordinary here. The same rock obeying two completely different rulebooks. Film crews documenting future Mars missions will capture this moment constantly. A tossed water bottle sails farther than any camera operator expects on the first take. Editors back on Earth will need entirely new instincts for pacing those shots. Even storytelling about Mars must relearn timing once real footage arrives. Picture a Martian schoolyard decades from now, dust settling under lighter footsteps. Kids there measure a good throw in units Earth has never needed. 110 meters draws a shrug, not a cheer. Their bodies grew up trusting Martian gravity, the same way Earth kids trust their own. Sports themselves may need entirely new rules once Mars fills with colonists. A baseball diamond built to Earth dimensions turns into a joke overnight. Every fence, every boundary line, every scoring distance demands complete Martian recalculation. Entire games might be invented specifically because Earth's versions simply stop working. Even this precise multiplier hides deeper unknowns beneath it. Mars' thin atmosphere still churns with dust storms nobody fully understands yet. Wind patterns there defy simple projectile math entirely. Gravity explains the extra 100 meters perfectly and completely. Gravity explains nothing about the planet's stranger unmapped mysteries. Every future mission carries instruments built to measure exactly this kind of gap. Scientists model how thrown objects drop tools, and bouncing rovers behave under Martian skies. Each new measurement refines the equations, slightly tightening numbers that once existed only in theory. Real boots on real Martian dust will confirm what mathematics predicted for decades. Compare this to Jupiter's moons, where gravity swings the opposite direction entirely. Io's surface pulls nearly as hard as Earth's, crushing any thrown object back down fast. Mars sits in between, weak enough to matter, strong enough to still feel like solid ground. That middle position makes Mars the perfect classroom for understanding gravity's raw power. Numbers on paper become muscle memory in boots on red dust. A rock thrown across that dust proves something larger than physics alone. It proves the rules that feel permanent on Earth exist only as local settings. Retention of this fact matters more than memorizing the equation itself. A tourist visiting Mars centuries from now will still feel the shock firsthand. Throwing a rock will remain the fastest way to feel a planet's true pull. No spacesuit sensor, no readout screen teaches gravity as honestly as a thrown stone. Change the planet beneath your boots, and gravity rewrites every falling object's story. Change the rulebook. Watch a child's game of catch become an entirely new kind of physics. Every equation solved on Mars uncovers new questions waiting underneath it. Those questions stretch farther across the unknown than any rock ever could.